Hello everyone, my name is Mohammed Bu Khamseen. This lesson is about downhole measurements. I'm gonna start by showing a video of what could potentially go wrong inside a wellbore to showcase why these measurements are important.
The lessons from Road Bore 204 are numerous and followed a sequence of events which, if any one had not taken place, the blowout would not have occurred. The burst delivery hose, which had to be renewed, the time taken to do that allowed the well to heat up and come under pressure. Another factor was not enough water was pumped to cool the well to quench the steam in the 2-meter cavity, just in the same way as it's possible to take a kettle off the boil by adding enough cold water. Today, improvements on similar jobs have been made as a direct result of the lessons learnt on bore 204. Casing is set and cemented at programmed depths, be the walls of the bore hot or cold. If that third string had been put down as scheduled, it's possible the well would have been saved. Drilling went on in cold conditions. When the bit dropped that critical 2 meters, the inference was it was into a hot zone. Since no casing was there to contain the pressure, the steam found its own escape route. Up the well and out below the bottom of the second casing string, and probably along a fall to the surface. Nowadays, with this firmly in mind, procedure for drilling geothermal wells in new or unknown areas of New Zealand call for the added safety measure of a false protective sheathing when drilling even deeper into hot formations. The bore finally died in November of 1973, 13 years after its tumultuous birth. It left its 22-meter deep and 70-meter in diameter scar as witness to the disastrous sequence of events which triggered it.
That was a glimpse of what could go wrong in a geothermal well. Um, it's one of these, or the reason these measurements are essential for ensuring the safety during drilling and operation of the wells. Here's a sort of an outline of what we're going to talk about today in this lesson. We're going to start with downhole measurements, their types, how and why they're used. Then we'll learn about some examples of the mechanical and electronic instruments used in downhole measurements. After that, we'll move to flow measurements and get to know why they're used. Then we'll talk about some common issues regarding the practice of downhole measurements. So, the most important and the essential measurements that are frequently done are temperature, pressure, and flow. Well testing programs include these measurements during all stages, starting from drilling and continue on to well completion, then heating and production. And these data are obtained from these tests. They're usually used in conjunction with data from other drilling and production operations in order to infer some meaning from them. An example of downhole measurements are temperature and pressure logs. These are the most frequently performed as they are critical to the performance of the well. They can be measured along the full depth of the bore with no change to the well conditions, so you don't have to stop operation or halt anything. Another one is formation imaging. It helps us know the geography or the structure of the well bore by providing 3D images using technologies like ultrasonic or microresistivity. It's designed to find fractures and the geological formations down the well bore. One of its issues is that it has limitations due to the fluid inside the well bore, which interferes with the readings. Another example is something called the Go Devils. This measurement, it's also called sinker bar or gauge ring surveys. This measurement is a plug gauge that determines the drift diameter of the well casing and the liner. These parts are positioned in most wells, or I mean, not all of them, positioned perfectly vertical from the ground down, but they tend to drift from their position during operation. Um, the Go Devils are relatively inexpensive, yet they provide vital information for casing damage and mineral buildup within the wellbore. Um, Two other examples are casing evaluation logs and calipers, but will not go into detail with them. So, the instruments that we use to make these measurements. I'll start with mechanical instruments. First one is the Geothermal Graph. It's the first instrument ever designed for measuring temperature within the geothermal wells. It was developed in 1950 um, for exploration of the Wairakei field in New Zealand. That's the field where the rogue boar was, we saw in the video. Takes measurements through an expanding bimetal probe, which expands through thermal conductivity, and it makes traces on a carbon plate, and these traces are used to infer what the temperature was. The instrument was it's definitely outdated by now, and it was superseded by Cooster mechanical gauges, which we will talk about next. The Cooster KPG gauge, it's known for being a robust and inexpensive instrument. It utilizes an old design used in oil wells, but it delivers reliable results in geothermal wells. It fits into any well that has no blockages. All it needs is 32 mm diameter, and it requires minimal maintenance for temperatures up to 300 degrees Celsius. Over that, it would still be able to function, but would need maintenance more frequently. And the accuracy provided by this instrument is in the order of 1 degree Celsius, and for pressure it's 0.2%. Excuse me while the slides load. The most common electronic instrument used is the PTS, pressure temperature spinner. It provides data through either real-time E-line, that's like instantaneous values that the engineers get, or saved memory, which means that you'll have to wait until the instrument is pulled out physically and then you get the readings. It's contained inside a Dewar flask to maintain its temperature below 100 degrees Celsius. Above that, it wouldn't be able to function properly. It provides accuracy better than 1 degree Celsius and zero point 0.1 bar for pressure. Its downside is that it has limited downhole time due to its inability to function in high temperatures. Next, we have the flow measurements. The most common one is the spinner profiling. It's the same electronic tool mentioned earlier, the PTS. It's performed routinely during injection or production, and it's useful for assessing interzonal flows while the well is shut. It requires stable well status that puts constraints on variations in flow or conditions of the well, and it adds very little cost over the temperature and pressure measurements. Two other methods for flow are temperature profiling and tracer injection, but we will not go into detail about those. So the common issues. Depth measurement. So because instrument depth requires accuracy in counter system to be within 1,000th accuracy, you get issues when it comes to the measurement. The calibration, to overcome that, the calibration can be set up over the ground surface or by comparing against known casing lengths. Another issue is well deviation. Many wells are actually purposefully deviated from the vertical, and you need a distinction between true vertical depth and measured depth. Ideally, the elevation of the measurement points and the temperature correction for the expansion are used together. Another issue is wireline thermal expansion. It often reaches several meters longer when it's in deep hot wells, and the expansion can be given by this equation. Um, Alpha is the coefficient of expansion of the metal used in the wire. L is the length of the wire, and the T sub AV is the average temperature inside the well, and T sub O is the surface temperature. And worthwhile mentioning that the thermal expansion is greater than the elongation due to stress. So that's what we take into account, and stress is usually considered as negligible. Another issue is well stability. Unstable conditions due to surface leaks, they affect the validity of test data. So to overcome this issue, data is compared between the down log and up log. That's data taken as you're going down. Up log is data as you're going back up to the surface. The engineers ensure that they're identical to make sure everything is in order. Last but not least is instrument lag. Data could be offset while instruments moving down the well bore, just from regular defect in instruments or errors. And to overcome this, some PTS instruments include casing collar locator to reduce errors. So to wrap everything up, downhole measurements we talked about are performed periodically to obtain essential data for the operation of the wells using instruments like Geothermal Graph, Cooster, or the pressure temperature spinner. The effective use of the instruments provides the data within desired accuracy, as we mentioned, usually 1 degree Celsius, and for pressure either 0.2% or 0.1 bar for the electronic one. Some corrections are applied to account for things like the type of design and the performance in the well.